Welcome back again. In the last lecture we have discussed about the maximum principle, in fact strong maximum principle, which says that if you have a subharmonic function, it cannot have an interior maximum. Similarly, if superharmonic, it cannot have an interior non-constant interior minimum. If it is a harmonic, it cannot achieve more interior and maximum and minimum. So, from that we can immediately derive some what we call it a weak maximum principle. Okay. So, it is a kind of derivation. Assume, so let me write the statement. So, as again assume this is trivial. So, there is nothing much to prove, it follows immediately. Omega is a bounded region in R n, okay. And let u belongs to C2 of omega. So, you have twice differentiability in interior, but you have continuity up to the boundary. Then you have 1 if u is subharmonic, that implies what we have proved is that if u is subharmonic and C2 and is non constant, it cannot have an interior maximum. But if a bounded if a continuous function in a closed bounded domain has to have a maximum. So, that maximum has to be at the boundary. So, that is what we are. So, supremum of u over the domain omega, and it will become a maximum. Omega is open, so that may not have that one. So, on the omega bar it will have a maximum, that is true, and that maximum has to be achieved on the boundary. That is what we are telling, you see. So, you have to understand the theorem properly. So, the proof is over, that is the proof. So, if you have an interior maximum, so I am also giving you the proof, this is an obvious thing. So, supremum of u should be maximum of u, and that maximum has to be achieved on the boundary. The strong maximum principle says that it cannot be in the interior. So, then since it has to have a maximum including the boundary, it has to be the maximum at the boundary achieved. So, it is a similar result. If Laplacian of u less than or equal to 0, that implies infimum of u over omega is equal to minimum over minimum, and you write it infimum is achieved. U that is equal to minimum has to be achieved on the boundary. That is what the strong maximum principle. Strong maximum principle says it cannot have interior, but then it has to have, since it is a bounded closed domain. And the third one, if Laplacian of u equal to 0, that implies the u will be bounded by minimum and boundary. So, that implies from that 2 you can reduce that minimum over u over the boundary less than or equal to u of x, right, because minimum is thing, it has to be on the boundary achieved less than or equal to maximum of u on the boundary. So, this should be for all x in omega. So, you see, so the maximum principle, the power of maximum principle, you have a point-wise estimate. If you have a harmonic function, you can estimate by its boundary values, and in a PDE the boundary values are given to you. So, you are will get even if you cannot solve the equation, that immediately tells you about that the bound, a lower bound and an upper bound about the solution of a harmonic function. So, any harmonic function you take in a bounded domain, it will be estimated by its boundary value. In a PDE is concerned, boundary values are given to you. So, it will be estimated by the known values without solving it. It is a kind of a priori type estimates which you are deriving it. Okay. So, that is so the proof is complete already. Okay. So, these are called weak maximum, and it is not only weak maximum and minimum, both are there, weak maximum and minimum principles, you do that one. And as I say, there are such maximum minimum principles can also be derived for general second order elliptic and other operators also. But as I said, we are not going to give you anything, but then in our reference book we have given some nice examples of a thing. So, if I get time, I will come back and do something, but I do not think we will have sufficient time in this 20-hour course to derive all the proofs and theorems. But when you are studying this course, it is important that you also study something more than what we present here about other second order elliptic operators. Some cases are given in our book, and there are many interesting things in our in the other books, like as I mentioned in Gilbert Truding or in many other books here. Okay. So, with this I want to make start with some examples now. Two examples. One example requires more proof. I will sketch you the proof, but you complete or read the proof here. In general, maximum principles are not true, maximum principles are not true for higher order equation, not true for in general. There may be some special cases, true for higher order operators, higher order operators. Okay. So, you look at this example, consider this function ux equal to x into x minus 1 into x plus 1 for x in 0 1. Since this is a third degree polynomial, this immediately implies that it is a d power 4 u by dx power 4. This is equivalent to fourth order equation, right? Okay. But so the u satisfies this fourth order operator d power 4 by dx power 4, but u has a strict minimum, but u has a strict minimum at x equal to half, is an interior minimum. So, you see, even the first one variable case, this maximum principle is not true. The other result is not really an example, this is also an example, but it is more like a theorem. So, let me so let me also write in general maximum principles are not true for unbounded domains. Principles are not true in unbounded domains. Unbounded domains. But there is a very interesting example, but there is an interesting example, but we have the following example. Following positive result. Positive result. In general, it is not true, but there are some domain which I want to tell you a result. Okay. So, this is a theorem which as I said, now I am going to present few theorems without proof. In the short course, it is not possible to prove several theorems. So, we will make some of them, we will make only the statement, but then it is up to you to go and see the, but since I am not covering the proof here, that does not mean that you the first time learners should skip the proof. It is important that you study the proof. So, let me give you an upper half plane. This is upper half plane, okay, x1 x2 plane as you see, upper half plane, okay. And u belongs to C2 of omega is a bounded harmonic function. So, this is a positive results in the upper half plane, bounded harmonic function. Then okay, supremum of u, this is the result which mod u over omega bar, the entire upper half plane. This only tells that the supremum is attained at the boundary d omega. So, here in the previous case, let me go to a previous case, let me probably state one result, probably it will be helpful to you. So, an example here, why in unbounded domain it is not true. So, you again consider omega upper half plane, upper, this is an example for upper half plane, okay. And you look at u of x1 x2 equal to x2, okay. Then u is harmonic, then u is harmonic, okay, and u equal to 0 on the boundary. What is the boundary here in this case? This is the boundary, okay. This is your d omega. So, the maximum is not on the boundary. You see u x1 x2 x2 as increases, it increases. So, u is not the maximum is not attained, maximum is not on the boundary, maximum is not on the boundary. You can have in unbounded domain. So, where other case said that you have the maximum attained at the boundary. So, unbounded domains are generally true, but we have the result which we are doing is that you see you have a thing, and how if you happen to be a bounded harmonic function, the previous thing is that your u is not bounded. So, if you have a u C2 of omega in the upper half plane, this is a very special case, then the maximum is attained here. As I say that I am not going to prove it, I want to just sketch the proof here. Okay, I will give a sketch of the proof here. So, the idea is that you consider another function. This is not, it is a very, consider another function. This is any two dimensional case, Vx equal to ux. So, you work out the details. So, I will only ask you to work out the details here, okay. So, ux equal to minus epsilon by 2 log x1 square plus x2 plus 1 whole square, okay. If you look at it, you know that V is harmonic, that implies V is actually harmonic. Why it is harmonic? Of course, you can verify the harmonicity, but if you look at it, this is something like a fundamental solution, right? Something like, not exactly, fundamental solution, you see. So, you do not have to worry, but you can guess it, but you can actually prove this is a harmonic function, okay. So, epsilon is a harmonic function close to it. So, what I will do now, So, the sketch of the proof is, so you define a domain, so you have to write down, it is there in the book. So, you write down not exactly the semicircle, I will put minus a here, something less than a semicircle. So, you look at, I call this is your omega A. Okay. When you have this one, the thing is that, and you consider your V in this domain. Okay. So, you consider V here, V is defined everywhere. So, consider V in omega A, and you, which is a bounded domain, you see, bounded domain. Therefore, by our earlier maximum principle, the maximum is obtained, maximum of V is attained on d omega A. So, but d omega A has two boundary, one here gamma A, here gamma A1, and the boundary of omega is this full, this is your boundary of omega A. It consists of gamma 1A and gamma 2A. Okay, gamma 1A union gamma 2A. Okay, so the maximum is attained there. So, the important step in this, which I will not prove it, that is what you have to look into the book, or you prove yourself. It is not difficult to prove by yourself. Show that the maximum of V is not attained on curved boundary, is not attained on gamma 2A. Hence, it is attained on gamma 1 A1, and then take A tends to infinity or A large, you can this is proved some sort of a contradiction. If there is a maximum, you derive a contradiction. If there is a maximum attained on gamma 2A and take A large and derive a contradiction to show that the maximum of E is not attained in omega A. Okay. And then when epsilon tends to 0, show that so the maximum will be attained as epsilon tends to 0, show that the maximum of U is attained on the x axis. Okay. So, that is the theorem which you want to prove it. Okay. All right. So, please go through it carefully. So, that proof is I have, except the claim, I have proved everything. Only the claim you want to see that the maximum of V is not attained on this example. Okay. And then once you prove that, that is you just to do a small calculation. So, that is not a difficult thing, but you prove it, and then take epsilon tends to 0 and do that one. With this, I can prove the uniqueness of our. So, what are we trying to prove it? Uniqueness, this is the thing, uniqueness of boundary value problem. What is our boundary value problem? We have here minus Laplacian of U is equal to F in omega, that is our problem. U is equal to G on D. When I say uniqueness, we are not claiming there is a solution. That means there does not exist. So, the theorem is there exists at most one solution, at most, that is the theorem. Okay. There exists at most one solution. Okay. So, how do you prove it? That proof is trivial. How do you suppose U1, U2 are two solutions, then U equal to U1 minus U2 satisfies Laplacian of V equal to 0 in omega and V equal to 0 on the boundary of omega. That is it, right. Now apply maximum principle, apply the weak maximum principle, weak maximum minimum principles. What does that tell you? This will imply, okay, the minimum is 0. What is the minimum? Minimum of V over the boundary, not V, sorry, you have to write U equal to 0. So, minimum of U is less than or equal to Ux, this is equal to 0, less than or equal to maximum of Ux over the boundary, that is equal to 0, implies Ux identically 0 in omega. So, you have immediate uniqueness theorem. So, typically when you study partial differential equations, there are 3 questions: the existence, uniqueness, and then there is a third thing, what we call it regularity, which we will be discussing something soon. As I said, we will also discuss existence in the coming lectures. Uniqueness is what we have done now. And also I have remarked earlier, though as I said, now let me recall again, remarked, you proved if U is in C omega, this is not proved, U is in C omega satisfies, or this is rather a theorem. As I said, we will not prove it here right now, satisfies mean value property, that implies U is equal to C infinity. So, the main existence theorem, you may be demanding some regularity. So, when you are looking for a solution of your boundary value problem, we look for U is in C2, not more than that, because your operator is a second order operator. Okay. So, when you have a second order operator and you look for a solution in C2, because you are looking for a solution of Laplacian U equal to F and U equal to G. But after obtaining your solution U, you ask questions whether U is C3, U is C4 and U is C infinity. And these such questions, so after proving, you look for higher regularity in the obtained solution. Such results are called regularity results. And this is all the more important when we study solutions in the Hilbert space approach, which you will not see it here. For example, you study weak solutions and you look for weak solutions in some Hilbert spaces. So, initially you start with a weak formulation. So, this is just general remark before we go further. When you have a start with a different formulation, you look for a solution of your thing not in the regular spaces like C2, C3, C4 etc., or Helder spaces which you may see in the next course. You look for solutions in certain Hilbert spaces and then look for, after obtaining solutions in a certain Hilbert spaces, try to say something what we call it Sobolev spaces. You look for solutions and try to prove that solutions are in bigger better spaces rather. Using that results, try to prove that that U is actually a smooth solution. Okay. So, there is the regularity is also employed to prove the classical solution from weak solutions. Okay. So, here what I has mentioned is u is in C omega. What we have proved is that assuming u is in C2 of omega, twice differentiability n satisfies the mean value property, and then u is a C infinity, you proved that u is harmonic. Okay. This is something more than that. So, there is a nice proof using convolutions and modifiers that if without the assumption of u is C2, just u is continuous and mean value property, because the defined mean value property continuity is enough, because just integral of u. You can actually prove that u is C2, which can actually prove it, and hence it is harmonic. So, this implies that every harmonic function, even though you start with a C2 solution, end of it u is a C infinity function. So, this operator Laplacian is provides, so these are all some sort of a smoothing operator, and you see this in the introduction. I told you elliptic operators and heat operators have this smoothing operator, but you will see in the wave study of wave equation, it takes you the singularities are propagated. You cannot expect this operator to produce smooth solution. In fact, sometimes you lose your regularity. That is what we see when we have studied the Burger's equation. It can generate singularities. It can produce physically relevant non-smooth solutions. This is something like a kind of two different things for elliptic equations and the hyperbolic equation. Okay. So, let me proceed further. All right, after proving the uniqueness. So, I want to discuss something again. I will not be able to prove many of the results. So, I just want to talk to you about what is a so what I have just stated, maybe I will not have a time here now. So, what you have with all these results, with the remarks, if u is harmonic, which gives you implies u is C infinity. So, you can talk about u prime etc. here, but what in the next class what I am going to prove is that actually u is analytic. Analyticity is a stronger property, which I am going to tell. Okay. Analytic, that means it has a power series expansion. Power series expansion. I will tell you what is the real analytic functions, and then I will move on to, again as I said, I will not prove each and every step, but I will try to give you the important steps in the analysis. Okay. So, since we have few minutes left, but I think we start fresh by giving you the definition of a proper analytic functions and give you what exactly you have to prove it. Okay. So, you see, starting with an continuous function satisfies the mean value property, it becomes a harmonic function, it becomes C infinity, and then it becomes analytic. Okay. So, it is a powerful thing. So, with this I will stop this lecture and we will continue. Okay. Thank you.